Hello, and welcome back to Teacher Gimble's channel. Today we'll be going over Geometry Unit 2, Lesson 5 Practice Problems. If you like this video, please make sure to like and subscribe. The button somewhere down here. I think it's on this side. Also, we just came out with a new website, rateyourprincipal.org. So if you are a teacher or anybody associated with the school, go to rateyourprincipal.org, check out your principal, and see what their reviews look like. And if you want to, post your own. Let's get started. Problem number 1. Write a sequence of rigid motions that takes figure ABC to figure DEF. So we're going that direction. I can see that C corresponds with F, so I would first translate and put C on top of F. Then this figure is going to come down and look something along the lines of this. Again, my drawing's not so great, but you get the vision of it. I would then rotate, I would say by roughly a 60-degree angle. Where's my clock? I'm going this direction. My clock goes tick, tick, tick that direction, so that is counterclockwise. I would rotate 60 degrees counterclockwise until A lines up with D, and then they would be on top of each other. And I'm done. Let's go on to the next question. Problem number 2. Prove the circle centered at A is congruent to the circle centered at C. Well, circles, you measure circles by their radius. The radius is the same in every single direction. That's my bad radius, showing it's the same in every direction. And the radius here is the same as the radius there. If the radiuses are congruent, the circles are congruent, and we're done. Another way to do this, using rigid motion, is if we sent C over to A, we would see that the two circles line up perfectly, exactly on top of each other. And using that translation's rigid motion, therefore the circles are congruent. Problem number 3. Which conjecture is possible to prove? A conjecture is a math guess or a math hypothesis. We're saying we think this is true and then we have to prove it. Math is fun because you can actually prove things. A. All quadrilaterals with at least one side length of 3 are congruent. The way I like proving conjectures is I like trying to figure out different scenarios. Here are two quadrilaterals. They each have a side length of 3. Are they congruent? Nope. It is not true. All rectangles with at least one side length 3 are congruent. Well, these are rectangles. They have both one side length 3. They are not congruent. Nope. All rhombuses with at least one side length 3 are congruent. Well, let's draw a rhombus. A rhombus has all sides are the same. So if one side's 3, all the sides are 3. But this guy right here is also a rhombus. He happens to be a square as well. They are not congruent because they have different angles, so nope. All squares with at least one side length 3 are congruent. Well, all four sides have to be congruent because it's a square, so all 4 sides are congruent. It's a square, so all 4 angles are congruent and are 90 degrees. So however you draw it, all the angles, and if one side is 3, all the sides are 3, all of the angles and all of the corners, all of the angles and all of the sides of all of the squares with a side length of 3 are going to be congruent. So when I have conjectures, I always try to find the exception to the rule. And if the exception to the rule is there, I know the conjecture is not true or cannot be proved. Or it can be disproved, which is the same thing as cannot be proved. Isn't math fun? Problem number 4. Match each statement using only the information shown in the pair of congruent triangles. The two sides and the included angle of one triangle are congruent to the two sides and the included angle of another triangle. So I'm going to mark up my triangles first to make this easy. I see this angle is congruent to that angle, so we have an angle. I see this side is congruent to that side, so we have a side. And I see this angle is congruent to that angle, so we have an angle. Angle, side, angle. Here we have a side congruent to a side. I'm matching the dashes. The dashes are sides. A side congruent to a side. Matching the dashes again. The dashes represent sides, not angles. And this side congruent to that side. So we have a side, side, side situation. Now here, a side congruent to a side. Here, an angle congruent to an angle, because they both have one dash in them. And here, two dashes, a side, and a side. So we have a side, angle, side. So we're looking for two sides in the included angle. Two sides, 1, 2, in the included angle, the angle in between, they match. For this one, two angles in the included side of one triangle are congruent to two angles that included side of another triangle. Angle, angle, and a side in between. Finally, two triangles, there are three pairs of congruent sides. 1, 2, 3, 1, 2, 3. And we're done. I always like marking up my triangles first because that helps me visualize it better. We're moving on to problem number 5. Wow, this is going fast. You are really smart. I'm talking to you, not myself. Triangle HEF is the image of triangle HGF after reflection over line FH. So we have line FH. Let's change colors. Let's make sure we're writing. And HEF is the image of triangle HGF after the reflection. So it's flipped over on top. Write a congruent statement for the two triangles. So we have HEF is a triangle, is congruent. Well, HE matches up with HG, so it would have to be triangle HGF. And that's our congruent statement. And we're done. Let's go on to the next one. Problem number 6. Triangle ABC is congruent to triangle EDF. So we got ABC, EDF. So Lynn knows that there is a sequence of rigid motion that brings ABC to EDF. Yes, so Lynn is correct. Select all the statements that are true after the transformation. So we are looking for what stacks on top of what. So ABC is going to go on top of EDF. So A matches up with E. So A is going to be matched up with E. B matches up with D because they're both the middle letters. And then C is going to match up with F. So in this case, it looks like actually this triangle kind of zoomed around, came like that, and then flipped or rotated to go on top because it's the ABC, and it rotated and it flipped. It's always important to match up your letters. And when you have a congruency statement, ABC is congruent to EDF, it's easier to do this. D matched up with B. So visualize this triangle went on top of that one, kind of using a reflection, so we know it's flipped. Does A correspond with F? No, A corresponds with E. Does angle B correspond with angle D? Angle B, D, yep. Does angle C correspond with angle E? Nope, C corresponds with F. Segment BA, does he correspond with DE? BADE, BADE, yep. And then does segment BC correspond with FE? Does BC correspond with FE? No, BC corresponds with DF. So this is incorrect. All right, if you're having a hard time, I recommend you grab a sheet of tracing paper and try this out on your own. We are now going to go on to problem number 7. This design began from the construction of a regular hexagon. A regular hexagon means all the sides of the hexagon are the same length. So AB is the same length as BC, the same length as CD, the same length as DD, the same length as F, the same length as A. Is quadrilateral JKLO congruent to the two other quadrilaterals? So JKLO, is he congruent to the two other quadrilaterals? Explain how you know. So when they're talking about the two other quadrilaterals, so we got this one, and I think we're talking about this one and this one. Well, we know that ABCDEF is a regular quadrilateral, so all these side lengths are the same. And it looks like O is the center. Do we know O is the center? Would O not be the center? Theoretically, O could not be the center. I feel like the answer will tell us AC has to line up, but they could be like this could not be a regular hexagon. We're gonna go over here. We're gonna look at the answer because I don't want to give you the wrong answer. We're looking at the practice, and we're gonna go all the way down and see what's up. It says it is congruent because it is reflected and taken over. So Sample response. Let's see what they say. Quadrilateral JKLO is congruent to quadrilateral JIHO, and quadrilateral LGHO. So they are talking about the three we're talking about. When JKLO is reflected across segment OJ, so we're saying when we reflect across him, he's going to stack right up there. And then when we reflect across OL, which is right here, he's going to stack right up there perfectly. And so they are all congruent. So that is the answer it gives to you. Now, does it ever say O is perfectly the center? No. So I would actually argue with that answer as a math teacher, but in this case, it is saying that this is a reflection of this is a reflection of that. So therefore, it has to be congruent. I guess the fact that it says it began from a construction of a regular hexagon implies that they use the center to construct the regular hexagon. But again, mathematics sometimes can be argued, and that is the case with this question. If you like this video, please make sure to like and subscribe. If you want more videos, put them in the comment. And if you're a teacher, make sure to check out rateyourprincipal.org. I will see you in the next video.